Welcome back to my channel mga ka-design. Today I present the new Engineering Design Innovation Part 2, Simplified Method of Analyzing and Designing Reinforced Concrete Columns. So when you have a structural framework of building, the conventional way of structural analysis is to analyze its structural frames of the framework and determine the stresses in its structural elements from gravity loads using moment distribution and from seismic loads using portal method and cantilever method. For gravity loads analysis, this is the example of moment distribution method. For seismic load analysis, this is the example of portal method to determine the stresses of its members of frames. This process will take you months to arrive in your final stresses. Because you are going to analyze its frame one by one and steps by steps. But YAZE has devised a simplified method for structural frame analysis, which in less than an hour you can see the results of your analysis and design by selecting a critical member that will be analyzed and designed, like this one. This simplified method is a practical solution and is based upon the real events. It is a reconfiguration of the theoretical method with a factual actual application to enhance and develop powerful method of design analysis. So this photo shows the collapse of buildings in earthquakes and their structural system all failed at the bottom of pit of the structures where the ground columns are located. So as you can see, these buildings collapse at their base. So when you go yourself to investigate what was happened to the columns of these structures, why does it fail? The photos below will tell you the answers. So when you study the seismograph, the displacement and the amplitude of earthquake, and investigate what was happened to the columns, you will find out that it fails in the three types of column failure: by buckling, compression, and shear failure. Compression failure happens for short columns. Buckling, shear failure happen for long columns. So in this case, it shows no indication of flexural moment failure, but completely an axial forces failure. Why is it the theoretical approach? There are moment distribution and portal or cantilever method for seismic analysis. But in actual incidents, the failure were mostly caused by axial forces in primary earthquake loads. So here's the key. First, we must look at the beam. Suspended beams are designed with some factors. First, the concrete alone has flexural strength capacity to withstand the gravity loads. Second, other factors are LRFD load factor safety and reduction factors that amplify the strength of suspended beams. Due to these factors in item number 1 and item number 2, suspended beam design is over-designed of about 150 to 200% as compared with the plain unfactored stresses imposed on it. That's why it does not transfer or transmit any flexural moment to column in its actual condition. And the column has become purely axially loaded column even there is a shaking manifested by an earthquake. But why the column still fails even if it has enough safety factors? So we have to reinvestigate. First, check the capacity of your column section if it is correct. If okay, check the horizontal tie stirrups of column. I'm sure you will not get the right solution because the column is purely axially loaded and it does not have a shear stress. Then how you find the correct solution of determining the spacing of ties if the column is axially loaded and has no stresses? We will answer that later. Then third, determine the location of the most critical section of column from its whole unsupported length in which failure has occurred the most. The critical zone for horizontal ties stirrups shall be properly provided of sufficient ties. So this is the method of YAZE. YAZE method of approximating the equivalent shear stress for purely axially loaded column. The equivalent shear stress is determined by proportionating the magnitude of axial load with the approximate distance of horizontal displacement where in that point the concrete starts to break. So this is the axial load. This is the equivalent shear stress from axial load. So by proportionating the axial load to this equivalent shear from the horizontal displacement, this relationship of these two, we can arrive the new formula or equation for this equivalent shear stress. This equation will be used for my design software. Let's go to my design software. So this is my design software. I devised this one to design a reinforced concrete column. So this design software will be my next presentation. Okay, that's all for my presentation. Thank you.